I'm Benjamin Jailly. I'm a PhD student in Telecom Etienne. It's a French engineering school. And I'm going to present you OCELOT. It's our project. So it comes from a research project, mainly for e-education. We'll see what it's all about. So here is a bit of the plan of my presentation. We'll first talk about online laboratories, because it's what it's all about. Next, we will see a bit of the architecture of the project, and then our ongoing works, because OCELOT is at the incubator phase. And for now on, we can say it's still an alpha release, a pre-alpha release version of the framework. So we can divide the laboratories in four kinds: the local labs, the virtual labs, the remote labs, and the hybrid labs. The first, the local labs. So the user is learning with a device on site, in situ. The device can be connected to a local computer to control the device. We got the virtual labs, where everything is virtualized. It can be online or not, or everything stored on the PC of the user. We got the remote labs, where you only control the device through the internet. And then the hybrid labs, when you have the control on the real device and a part of simulation. What we try to address with OCELOT is those two kinds of labs, the remote labs and the hybrid labs. The primary reason why we want to control this kind of devices on the internet is the cost. The financial cost, because we want to, at least for researcher and in learning institute, we want to share some devices which are very expensive. And also the geographical constraint. For example, when you have students who are learning abroad during 1 year, we want maybe to do some kind of laboratory session abroad. These are not the only reasons. We can say security, availability, collaboration, limited number of people in the same room. Sometimes the device cannot be accessed by 20 people. And also the computer-assisted lab. Let's say the computer tries to say to you, you've done that action, maybe you can do that one after that. We'll talk about this later. So the main actors are the industry, for example, remote maintenance, the research in order to, like I said, share resources, or the education for e-learning. But the problem, it's really time-consuming to build that kind of solution. Also, the people who need that kind of solution are not usually every time programmers. So we need to give them the possibility to create their online labs without programming skills. And the third main issue is when we design an online lab, usually we're using a web form, but it does not represent the real device as it should be. We'll talk about this a bit after. So let's have a look at the architecture of the framework. These are the two approaches that are usually done for online labs. We have the mixed interaction, what we call mixed interaction. So you have the web application when you pass your command, and the device is captured by an IP camera, and you can see the feedback in the web form. We have the exclusive application, where all the interface of the device is represented in the web form. What we try to achieve here is an interactive multimedia. When the idea is you capture the device itself, and at the client side you have like a interactive multimedia, and you can interact with the device by clicking in the video. On the client side, we are using the MPEG binary format for scenes. It's a standard by the MPEG group. It's a scene descriptor. The representation is a hierarchical tree, like the syntax can be XML or YAML. The scene can be compressed and multiplexed within an MP4 file. So MP4 file, I think you all know that kind of format when you're looking at DVDs on your DVDs or DVX on your computers. And also another interesting thing is that you can embed ECMAScript inside the BIFs, so that they can easily design complex behavior on the client. The BIFs player, we're using the Osmo 4 player, which is part of the JPAC project, another open source project. So how it works? You have the IP camera, which is capturing the device. We have it delivers an H.264 stream, or also known as MPEG-4 AVC for multimedia guys. We have the decoder block, which decodes it. Inside the processing block, we recognize the device, and we extract a zone that the user defines. Important. Everything is re-encoded, and then with a Darming streaming server, we broadcast everything to the client with the RTSP protocol. In the framework, we provide an authoring tool to create your interactive multimedia. As I said here, in the processing block, we recognize the device, and we extract a zone that we define interesting. Here, for that kind of device, the only real video part is the display of the device. That's why we are only cropping that part of the device and stream it to the client. The other stuff are graphics that are computed within the BIFs, thanks to the authoring tool. On the middleware part, we're using the Jonas application server. Everything, all the commands are stored in the GMS queue, which is implemented in the JORAM. And everything is then interpreted, and the corresponding hardware function is sent to the client. For the push message, we defined a notification system for handling collaboration. The idea is when multiple users are using the same device in the same time, we need some kind of notification to say that user have done that. So we enriched the BIFs with the WebSocket protocol in order to support the push-pull. On the driver side, for now on, we're only working with measurement devices. So we are using the interchangeable virtual instruments. This kind of drivers, it defines some classes of instruments, like oscilloscope, spectrum analyzer, the one you just saw. And the idea is, once you develop a driver for that, a program which can control one device of one class, you just can unplug it and plug another device of another vendor, and it should work. There's a lot of constructors that can provide that kind of classes, like Rode Schwarz, National Instrument, Agilent, HP, Tektronix also. So this is the interface the user can see at the end. So you see the display is the real display captured by the IP camera. On the background, we have a JPEG image. All the buttons are also graphics in the BIFs, and we provide a telepresence indicator. A telepresence indicator to say, okay, which users are connected in the same time, and also a chat in order to user to communicate together. It's also working on mobile devices. We've done some tests, a tablet running on Android and Galaxy Tab, so Galaxy S also running on Android. Ongoing works. So as I said, it's still a project in the incubation phase. We have a lot of work to do inside. So the project is called OCELOT. It's an open collaborative environment for the leverage of online instrumentation. As I said, it comes from research. It's incubated at the OW2, of course. And the current state is alpha 0.1. The license is LGPL. So our ongoing works on the multimedia is to adapt the multimedia depending on the user context. For example, the CPU available, the OS, because maybe the interface is not the same on mobile devices or on computer, on the available bandwidth. We also want to adapt the multimedia depending on procedures, for example, for maintenance, remote maintenance, and also the support for 3D scenes. The good part of MPEG BIFs is that it supports 3D scenes. So we want to add that feature on the framework. On the middleware side, we would like to put the streaming server inside the Jonas middleware, because for now we are using the Darwin streaming server, and we would like to embed it in the whole middleware, not using a third-party library. On the driver side, we would like to do a kind of driver introspection, like see if we can automatically guess what kind of available functions are for the devices. Also implement different kind of IVA classes, because for now we're hardly working on a spectrum analyzer. And we would like also to find some other use case. We're working on an interactive IPTV application. Okay, thank you for listening to this presentation.